He's bringing on the fun. Oh, Nickelodeon.
Alright guys, we're back. Picking up the second video here with strong acids and strong bases versus weak acids and weak bases. Is there really a difference, Mr. Bunting?
Yeah, there's a difference. That's why we classify them as strong and weak.
Okay. So what would I really be looking for if I'm trying to identify a strong acid or a strong base?
You're going to be looking for the ions that are formed.
Okay.
Is that the answer you wanted?
Sure. Yeah, so the more ions, I guess, would be a stronger acid, stronger base.
Right.
Is that right?
Mm-hmm.
So it's kind of like an electrolyte, maybe?
Those are definitely electrolytes.
Okay. So a strong acid and a strong base we would define as one that completely ionizes?
Completely ionizes. Which means there's nothing left of the original compound.
So it totally splits apart.
Totally splits.
So a weak acid or a base, I'm guessing they would kind of stay together a little bit.
Mm-hmm. So like kind of ionized.
So partially.
Partially. That would be a better word
That's
than kind of.
kind of. Kind of ionizes. So partially ionizes. I'm guessing there's a list of these that we need to remember, right?
Right.
And strong acids, there's actually just 7 of them. And they will start with
Hydrochloric.
chloric.
Hydroiodic.
Okay. Like the hello acid.
Yeah, hello acid.
Awesome.
Hydrobromic.
All right.
Chloric.
Chloric.
Sulfuric.
Sulfuric. Okay.
Nitric.
Nitric. And one more.
Hypochloric.
Awesome.
So all the other ones, if you see anything else, it would be considered weak. So we don't need to memorize anything there, right?
So just know these 7.
Right.
And we're good.
Everything else would be the opposite.
All right. Cool. Strong bases.
Strong bases are a little bit easier. It's any group 1 and 2 metal, except for beryllium and magnesium.
So any group 1 and group 2 hydroxide, except beryllium and magnesium. Awesome. So the alkali metals and alkaline earth metals, for those of you that have memorized those names. So we're good to go there.
All right, we're good. Let's go on, see where this takes us.
Okay, so we got definitions here. Again, there's a couple different definitions for acids and bases. Who's this Arrhenius guy? What is that all about? He talks about acids and bases, I'm guessing.
Mm-hmm.
And he defines acids and bases how?
He describes an acid as anything that produces a hydrogen ion.
Okay. So this is all based on ions. The H plus and OH minus, right?
Mm-hmm. That would be your basis.
So any substance that produces hydronium ion or hydrogen ion in solution. Okay.
Okay. You want to go do bases?
And bases would be any
hydroxide ions. All right.
So
what's an example of a good Arrhenius acid?
So an Arrhenius acid, well, I'm going to go with one of those strong acids that we talked about.
Okay.
And let's use maybe nitric.
Ooh, nitric acid. Now what do we do from here? If it's in solution, what do we do with that?
Well,
how do I know that produces hydrogen ions?
Well, I know it's going to react with water, correct?
Okay. Okay.
So I'm going to add water here, right?
Okay.
And then if I produce that H plus ion, it's actually going to look like, am I correct here?
There it is.
And then the nitride, or nitride.
There it is.
Does it match up there?
Matches
So
up
this
there.
is actually the H plus or hydronium. You may hear us call it this.
Yeah, that's worth knowing.
Okay.
You'll see that a lot. What about a good base?
A good base. Let's. How about barium hydroxide?
Barium's a good hydroxide.
Barium hydroxide. And I remember from our electrolyte unit that they don't actually react with water, right? So in the presence of water, they're going to just split apart or dissociate.
Right.
Okay. And that would give me barium and hydroxide. And I know that barium is a +2 because it's a group 2 metal, and hydroxide is a -1. So I would actually have 2 of these.
Yep. All right. Let's look at the Bronsted-Lowry. What would be the Bronsted-Lowry definition?
Well, I think that Bronsted-Lowry kind of expanded Arrhenius's definition and said that it's not just the H ion, but it's anything that donates a proton. Right?
That sounds right to me. This one deals with donation of ions.
Donates a proton. So acids, I'm assuming that they produce that hydrogen ion, so they will donate a proton, right?
So we're going to call those proton donors.
Okay. And that would make bases proton.
Well, if one is donating, the other one has to accept it.
Yeah.
So
okay.
proton acceptors.
Well, okay, so if a base produces hydroxide, but now we talk about Bronsted-Lowry and it's a proton acceptor. If hydroxide accepts a proton, it actually becomes water.
Water. Mm-hmm. That'd be a really good acid-base reaction. Also called a
Neutralization
reaction because
Awesome.
water is neutral. So a good example of a acid is anything that starts with H. So let's just go with HCl. It's going to donate that proton. A good base would be our plain Jane sodium hydroxide, NaOH. So if we put those two together, HCl plus sodium hydroxide, sorry, we're going to have base, it's going to yield the H from the acid and the OH from the base will form water, H2O, and then the other two things will form the salt. So we can talk about the sodium combining with the chlorine to form sodium chloride.
Okay, so the positive ion from the acid joins with the negative ion of the base,
Mm-hmm.
and vice versa.
Just like with every other reaction.
Awesome. I think I can work with that.
All right. Let's move on
Okay.
then.
What amphoteric? So
It's a weird word.
it is a weird word. You know what? I've seen that prefix before in biology, like when we're talking about amphibians.
Ooh, amphibians. What are those?
Those animals that kind of live both in the water and on land.
Oh,
So they can actually be two things, right?
Interesting. So how do we apply that to what we're learning now, with acids and bases?
Well, I'm thinking that if it's amphoteric, it could probably act as an acid or a base.
Ah, so it can go either way and be just as happy.
Yep.
Oh, those, I think those would be kind of rare. Are they kind of rare?
I think there's only one
There's only-
substance.
Okay. What's that going to be?
And it's that dihydrogen monoxide
Ooh,
thing.
dihydrogen monoxide, just like with the frog on water.
Yep.
Interesting.
So H2O.
All right.
Amphoteric. It can act as an acid or it can act as a base, because remember it can either donate a proton or accept one, right?
Mm-hmm. I think that's something that's worth memorizing. I might star that. Might come back to it a little bit. Oh, look at that. Starred for you.
All right, so acids, ionize. They ionize in water to form hydronium or hydrogen ions, right?
Yeah, either way. We just went over this, didn't we?
We did.
If we're going over it twice, is it going to be important?
I think so.
Oh, okay.
I think so.
Okay. Welcome to PowerPoint.
So, do we really need to do another example here? So it's really
let's
just
let them do an example of their own. Let's,
okay. We'll check these examples as you guys come into class. So just think of an example of remember, anything that would ionize in water to produce a hydrogen ion.
mm-hmm.
And a base would dissociate
Okay. Okay.
because it doesn't actually react with the water, right?
Mm-hmm.
Dissociate in water to form hydroxide.
So acids always got to do with hydrogen. Bases always got to do with hydroxide. It's a good common theme we got going on here.
Okay.
You want to let them do that one as well on their own? Just
Yep.
pick any old base and dissociate that thing.
Any base, dissociate it into the positive and negative ions.
All right. I don't think that's asking too much.
Okay, and the practice, right? The ionization reaction for nitric acid. I think we've already done this.
I think we did that exact practice problem.
Well, you know what? Let's just
Okay, let's just do it one
fly
time.
through this. So notice the ions balance.
Mm-hmm. That's good to know.
And sulfuric acid,
H2SO4.
assuming both protons.
It's important.
So
How is that going to change things? Anything different than what you would expect it to be?
well, it should just give me more ions.
Okay.
I would think.
Okay.
So H3O, and then sulfate, but the charges don't balance.
Oh no. What do we do?
So now I need 2 of those,
Okay.
and we should be
that
good.
works. Yeah. Perfect.
All right, cool.
All right.
Dissociation of potassium hydroxide, pretty straightforward here. Ooh, look, I'm going to base to blue. We're getting fancy. Potassium is going to...
Hydroxide. That one's gonna be difficult. There will be music playing.
Neutralization reactions. So if it's neutralization, and
Neutral.
I'm going to be creating
Neutral.
a neutral
Neutral.
substance.
What's that really common neutral substance we're going to talk about a lot? It's kind of a important thing. Had a whole video on it from the last unit.
Thinking
That's the one.
back in
That's,
talking about
that's kind
that
of an
guy.
important thing. It's like we're water-based creatures or something.
So a neutralization reaction is anything that produces water.
Okay.
Is that right?
That's right.
Okay, so I have an acid and a base,
The base.
and those two come together.
Mm-hmm.
So you know what? Let's just go over here to these examples. So H2SO4 and potassium hydroxide. Sulfuric acid, potassium hydroxide. Remember that 2 is supposed to be there.
Should be a subscript or 2.
So that's going to produce, my hydrogen is going to go with hydroxide and produce.
We recognize an acid reacting with a base. We can always go ahead and start off by writing out water. You know
Okay.
it's going to have to be there.
So the water is going to be there, and then I just need to take my positive ion and my negative ion and put them together, right?
The positive ion always goes first, right, Coach Miller?
That's right. Positive potassium metal first, and I know potassium's a +1, sulfate's a -2, so I'll balance it out.
There we go. Perfect. Beautiful.
All right, and do the same thing here. Get my water and aluminum nitrate. Ooh. Remember to keep nitrate in parentheses. So, and then we got to balance these.
Yeah,
So if we balance them, there'll be a 2 there, and there's a 4, 2, 2, 2, 2. All right. And 3 here.
Beautiful. All right.
So neutralization reaction, we actually treat it like any other reaction. We have to balance it out.
Mhm.
And it's not just ions.
Right.
Awesome.
Always make sure it's balanced.
Okay. I can do that.
All right. Hope so.
Precipitation reaction. I remember this word.
What was a precipitate again, though?
So, precipitate
In case we haven't caught on yet.
is that substance that falls out of solution, so it's not soluble.
It's
Or
not soluble
insoluble.
product. Insoluble product. All right. All right. So it'd be like those things we did in the last lab where we mixed two liquids in a solid form. That solid was that insoluble product, right?
Okay. So all that stuff that fell to the bottom of the little well
Mhm.
plate.
Okay.
I gotcha. So what we would look for is anything that is insoluble over here.
Mhm.
And they have to be our products.
Right. Focusing just on the products now, guys.
Okay,
So-
so sodium chloride. I know salt is definitely soluble.
Mm-hmm.
So I'm going to go to cobalt
Two.
carbonate.
Cobalt 2.
Cobalt 2.
Mm.
Carbonate is
Right there.
insoluble unless it's bonded to ammonium or an alkali metal, and it's definitely not. So
Cobalt would be a transition metal, so that looks like it'd be our precipitate.
I'm going to call that our precipitate.
our insoluble product.
All right.
The next one is a little bit more difficult.
Okay. So
lead 2 iodide.
lead to iodide. So lead is here. It's
Well,
definitely
iodide is there.
or iodide is there. Yeah. And it's soluble unless it's bonded to silver, lead, or mercury.
Oh, we got a lead bond of that iodide. So is it still soluble?
So I'm going to go with no.
No. So that would be our
Say
insoluble precipitate.
That's definitely insoluble.
Do we need to check the other one now, or can we just always assume the other one's soluble?
We should probably check, but I would assume that
It's a
it
nitrate.
would
So,
be.
yeah.
Nitrate, no
Nitrate.
exceptions. We're good.
All right. Wasn't as near as hard as it looked.
All right, so any precipitation reaction, we're just going to simply be looking for something that's insoluble on the right side.
Right. Take a look. If you don't see an acid or a base, this would be the next thing to look for.
Okay.
Okay.
Oxidation. What in the world are we talking about here? Oxidation and reduction.
These seem like one happens when the other one happens. Do these go together?
You know
What
what?
you said?
I think I remember from my chemistry classes that oxidation can't happen unless reduction happens.
Okay, so what is oxidation?
So oxidation is when the oxidation number of a substance actually goes up, right?
What is an oxidation number again? That's a big fancy word.
Or a charge.
Charge. Okay, so
And if the charge goes up, that means we're losing something negative because our charge gets more positive.
that would be
So
electrons.
Yeah. So we lose electrons in oxidation.
Okay, so a lot of concepts coming together with this one little word.
Okay, so oxidation is the loss of electrons.
All right, cool.
And reduction,
Would be the opposite.
I guess,
so
would be gaining electrons.
All right.
It's kind of a play on words there
Mhm.
because, we're gaining electrons, but we're actually reducing the oxidation number.
Right. We're losing charge in that state.
Okay.
Okay. So is there a good little mnemonic that goes along with this, or good way to remember which one's which?
Yeah, you know what? I remember. Oil rig.
Oil rig. What does that stand? What?
So
How does that help me?
oxidation
Okay.
is loss,
Okay. Loss of what? Okay.
and reduction is gain.
All right. We're talking about electrons when we're doing these, not charge. Well, in essence, charge.
So oxidation, you lose electrons. Reduction is the gain of electrons.
Oil rig. Something worth memorizing. Keep you straight.
All right. So we can jump into some practice here.
All right.
And anytime we're looking, how are we supposed to identify in oxidation reduction or something like that.
Well, it gets a lot more complicated than this eventually, but right now, if I look at this and I see lithium, and I see a lithium with a +1, and then plus an electron. So there's two different ways you can look at it. Which way do you look at this, or do you look at that?
I generally look at the element,
Okay.
but we
Which
can look
way?
at either way. We can do both ways.
Okay.
So if I'm looking at lithium, and lithium is definitely has no charge here, right?
Neutral. Okay.
And now it has a positive charge, so obviously went up.
Okay.
So I would call that oxidation.
Oxidation because it lost electrons.
Yeah, so
I look at the electron here. It's definitely in the products, which means it lost electrons. A little different way of thinking it, but some of your minds work like that. So either way is fine.
okay, so if it gives off the electron,
Mhm.
then yeah, oxidation is lost.
It's going away.
Okay. And I'm guessing since we did an oxidation, this would be a reduction.
Right.
But
But you see the difference.
So-
One formed a positive charge,
the other one went down.
the other one went down. And then also, you also have your 2 electrons here as a reactant.
Yeah, so it's actually gaining those electrons.
Gain those electrons.
And that would be reduction. Cool.
All right. Let's
So
see.
that's if they're by themselves.
Mhm.
But now we have to look at them together. And this kind of becomes a little more difficult.
Okay, do it. Well, let's see what we can do.
All right, so H plus, which is hydrogen gas,
Okay.
reacts with chlorine gas, and that gives me HCl, hydrochloric acid. So, I definitely see that anytime there's an element by itself, or if I remember correctly, anytime there's an element by itself, it can't have an oxidation.
Right. Those are all neutral. That's why they exist as diatomics, if we remember way back when.
Okay? Yeah, so they share and they balance each other out. All right?
But what happens when we join them together?
Well, anytime we join chlorine, I know for a fact chlorine's a group 17 element. It's always going to be -1.
Okay.
And hydrogen is always a +1.
Okay. So so something here has been oxidized and something else has been reduced, right?
Yep, because you have to have both of them happening at the same time.
Okay. Okay.
So
So-
hydrogen went from 0 to
+1.
+1.
So if it has a positive charge, it means it lost electrons, which means it would have been oxidized.
So H has been oxidized. And if
If hydrogen was
hydrogen was
oxidized,
oxidized, then
chlorine must have been reduced.
chlorine has to be reduced.
See that because it now has a negative charge, meaning that it gained electrons.
Cool. Well, you should be able to try the second one, or they should be able to try the second one on their own, don't you think?
All right, yeah.
And then they come back and check their work.
Okay, yeah.
Let me go ahead and run it. Right?
Yeah.